In this video, we will go over linear shift-invariant systems in 1D and 2D. Let's start by considering the 1D case. So we have a 1D system that takes a signal f, maybe a function of time, and transforms it into a signal g. Now, if this system is linear, this means that for any inputs f1 and f2 that give rise to corresponding outputs g1 and g2, if the input is a superposition of f1 and f2, perhaps scaled by some scalar constants a and b, then the output will be the exact same superposition of g1 and g2. And if the system is linear, this will be true for any f1 and f2 and any constants a and b. Now, a system is shift-invariant or time-invariant in the case of 1D systems where the signals are functions of time. If given a input f of t that gives an output g of t, if we shift our input, then we'll get the exact same output except shifted by the exact same amount that we have shifted our input. Now, linearity has very important properties for simplifying the characterization of a system. We can express our input f as a superposition of Dirac deltas. The Dirac delta is a very special generalized function that is zero everywhere except at the origin, and it has a large spike at the origin such that the integral of this function over all of time is equal to 1. The Dirac delta also has the important shifting property that allows us to express any function f as a superposition of shifted deltas that are weighted by the corresponding value of f at that point. Now, if we go back to our system description with output g and input f, and note that we have different indices here, t1 for f and t2 for g, to highlight the fact that our system H may operate on f over all time points in order to obtain the value of g at a single time point t2. If we insert the shifting property description of f into our system expression, we end up with an expression like this. And using linearity, we can now put the h inside the integral. So what we end up with is a description of g in terms of the effects of the system h on a bunch of shifted deltas, and each of them weighted by the value of the input f at that particular point. So we have simplified somewhat our description of h, because all we need to know about our system is the effect that it has on deltas shifted by different amounts. And if we know this, we'll be able to predict the output for any given input f, because f can be expressed as a superposition of shifted deltas. If in addition to being linear, our system is shift-invariant, then we can go back to our expression for the impulse response from last page, which was the response of our system to a shifted delta function, and simplify its expression as such using the definition of shift invariance. Now, if we insert this into our expression for g, we get a much simplified expression relating the input f and the output g, where these two are simply related by a convolution between the input and the impulse response of the system. In other words, all we need to know in order to fully characterize a linear shift-invariant or linear time-invariant system is knowledge of h, the impulse response, and the effect of this system is simply a convolution between the input f and the impulse response h. So let's move on to the 2D case. We can consider a 2D system that has an input f, which is a function of x and y, for instance, an image, and it produces an output signal G, for instance, a blurred or distorted version of that image. Now our system is linear, similarly to the 1D case, if, say, we have two inputs, F1 and F2, and they produce outputs, G1 and G2. If we have a superposition of inputs, then we end up with the same superposition of outputs. And again, this must be true for any inputs F1 and F2 and any scalar constants A and B. Similarly, our 2D system will be shift invariant if, let's say, we have an input f of x and y that gives rise to an output g of x and y. If we shift our input by some amount x0 in the x direction, some amount y0 in the y direction, then our output will be the same that it originally was, except shifted by the exact same amount as the input. Linearity applies also the same way as in the 1D case, so we can define the delta function in 2D as a function that's 0 everywhere except at the origin, but if we take the integral over the whole plane, this integral is equal to 1. So intuitively this is an infinitely narrow, infinitely tall impulse. We can also express our function f as a superposition of shifted delta functions that are shifted all over the plane and weighted by the corresponding value of the function f, and this is the so-called sifting property of the delta function, also in 2D. So going back to our expression for g, we can use the sifting property of the delta function in 2D to write out the input f. Using linearity, we can insert the effect of our system h inside the integral so that we can determine our output g simply by knowing the effect that our system has on a delta function that is shifted anywhere in the plane. In other words, in order to know our output g for any input f, all we need to know is the output h for a delta function that is shifted anywhere within the plane. Now, if our 2D system is not only linear but also shift invariant, then we can go back to our impulse response, which is the response of our 2D system to a delta function that's shifted by a certain amount, and we can define it simply as the impulse response to a delta function centered at 0, except shifted by the same amount as the delta function. We can insert this into our expression for g, which now becomes simply the 2D convolution between our input f and our impulse response h. This 2D convolution, sometimes it's expressed with a single asterisk, sometimes it's expressed with two asterisks. And similarly to the 1D case, all we need to characterize a 2D linear shift invariant system is knowledge of h, the impulse response, and the effect of this system is simply a 2D convolution between the input f and the impulse response h. We can view the effects of 2D convolution with a simple example. Here is an original image that's a representation of the letter E shown in 3D that's convolved with a small square, resulting in an image that has a certain amount of blurring. If instead of convolving it with a small square, we convolve it with a bigger square, then we end up with an image that is more blurred. And if instead of convolving it with a square, we convolve it with a circle, we end up with a output image that is also blurred, but with slightly different shape, particularly around the corners. This can be seen equivalently in the corresponding images. So here is the convolution with a small square, convolution with a larger square showing more blurring, and convolution with a circle also showing a lot of blurring but in slightly different shape.